All right, guys, I missed a few minutes of the lecture, but we're very early into the Chapter 4 PowerPoint, and it's stuff we've already talked about, like the selection structure. This is an if. It's a single alternative. And this is an if-else, the dual alternative. So we're using relational comparison operators. Pretty much, programming languages support 6 different types of relational operators. Now, am I going to ask you how many they support? No, but you know what they are, right? If x is less than 3, x is greater than 3, x is greater than or equal to 3, x is less than or equal to 3, x is equal to 3, and x not equal to 3, which I don't remember anymore, but in grade school or junior high or whatever, did we say that was not equal? I'm not sure. Anyways, like that. Those are the relational comparison operators. So, less than, greater than, less than or equal, greater than or equal, and not equal. I'm going to go and put a comment on this one. We know what that is, but this one is not equals. You can't put a space between those two, or else it breaks the syntax of it. Something to note is, if you think in terms of opposites, which of these should be paired? If you have if x is less than 3, its opposite is not if x greater than 3. They look like they're opposites. But the problem is this doesn't handle the edge case. What if it's exactly 3? If x is exactly 3 here, this evaluates to false because x is not less than 3. But its opposite should evaluate to false if x is equal to 3. So that is its opposite. So I'm going to put opposites. The opposite of less than is greater than or equal to. The opposite of greater than is less than or equal to. And the opposite of equals is not equals. That's why if you do something like this, if x is less than 0, print something. Right? And then if you do if x is greater than 0, print not freezing. That won't cover the case if it is equal to 0. If it is equal to 0, what's it going to print? Did I hear somebody say nothing? Hope so. Because that's what it's going to do, is nothing. Because if x is equal to 0, is 0 less than 0? No. Is 0 greater than 0? No. So it's not going to either print freezing or not freezing. And maybe that's what you want, but usually it's not. So if you were going to word your logic like that, you would want to put the opposite there so that it would catch the 0 case. Better yet would just be to put an else, right? Because then you know it's going to do the opposite. But I'll add that as a comment. You wouldn't use x greater than 0 because that would not handle the case where x equals exactly 0. Opposites. Let's correct the spelling of that. So these are known as binary operators. Most of your operators are, because they require 2 values. There we go. Every time we say binary, we think it requires 2 values. So just like addition and subtraction and multiplication and division, those are all binary math operators. Not because they work on ones and zeros, because they require 2 pieces of data to work on. Right? A plus B. 1 minus 2. 3 times C. That kind of stuff. The pieces of data are called operands. So if we want to talk like programmers, we'll use the term operands just so that we sound all fancy and stuff. The comparison operators are also binary operands. you know, if A is less than B, you have to have both of those. A and B are the operands. If you have A plus B, or 1 plus 2, 1 and 2 are the operands. Makes sense? So, I know that seems easy, but something that people like to write, which is not supported in the language, is what if you want to see if a number is between 1 and 10? If 1 is, don't do this isn't going to work, is less than or equal to the number which is less than or equal to 10. Maybe we did that in grade school or you know, junior high or high school or something like that. Maybe that syntax worked, but it doesn't work in computers. The reason why is that these are binary operands, meaning that they both have to have 2 values on either side of it. And it looks like they have 2 values, but they don't, because this one would be hooked up with that one, right? So that's one expression. That would evaluate to true or false. And if it was true, great. And then it's going to say is true less than 10. No, that doesn't work, because these are binary operands. We can't express a range in that fashion. If you wanted to word it for a computer, you would say if 1 is less than the number and the number is less than 10. That's valid syntax. Why does that work? Because now we do have 2 operators. Excuse me, 2 operands. Here's our operator. He's got 2 operands, 1 and number. Here's our operator. We've got 2 operands, number and 10. So this is invalid syntax, and this is valid syntax for checking for a range. Let me put that in caps just to reemphasize. I hate showing people the wrong thing, but I've seen, you know, enough people write code and turn it in and not wonder why it's not working, or answer that as a test question in that fashion, that I want you to see what not to do. All right, I don't think we need a big explanation of what these do. Greater than, yeah. Less than evaluates as true when the left operand is less than the right operand. We're just defining these in the jargon now. Greater than means evaluates as true when the left operand is greater than the right operand. So the left operand would be this thing on this side. The right operand would be the thing on this side. And so if A is in fact greater than 10, then the expression is true. But we know how less than and greater than works, I bet. We also know the difference between less than or equal to, I believe. Not equal to. They're showing in the textbook not equal to being that. I said that it was this. Exclamation mark. Unfortunately, no programming language I've ever seen supports the less than or this syntax. They all do this. So, if I ask you to list 6 comparison operators, it's okay if you list what the book does, but this is the one to burn in your brain. That's not equal to. So any decision can be made with only 3 types of comparisons. You're equal, you're greater than, or you're less than. But not equal involves thinking in double negatives. Sometimes you can kind of get your brain kind of warped because, you know, once you have too many, you know, knots in your logic, no pun intended. It's best to restrict the usage to if without an else. Only take an action when some comparison is false. If you were going to word something like this, and this is valid syntax, if not A is less than 3, do something else. Do something else. That's a silly way of wording it. You've got this not here, and it's messing with the logic. What does it mean? Well, it's saying that if A is not less than 3, do something. But we could rewrite that, right? We could, what is the opposite of less than according to our little list up there? The opposite of less than is, yeah, greater than or equal. So we could just do if A greater than or equal to 3, do something. Else, do something else. Maybe it doesn't send a light bulb off that this is easier to read than this. If it does, great. I just tend to write my expressions avoiding the not if I possibly can, because the way a lot of people's brains work is it's easier to parse. You can look at it and understand more immediately what it's doing, especially if it's a complex one, right? That one's pretty easy. But like I said, you can chain things that have several ors and ands and stuff like that, and it gets more difficult to understand if you have too many nots in it. So their suggestion is if you're going to use not or not equal, restrict that usage to a single alternative if. So like this, if A is not equal to 3, do something. Don't throw in else, do something else. That's their recommendation. And I'm going to just kind of go, I don't really see the point. Well, because we could rewrite it like this. If A is equal to 3, do something else, else do something. Instead of saying do something and then do something else, I'm going to make that do something 1 or do something 2. And, same logic here. We've written the opposite, so we're going to do them. Okay, this is identical logically to this. It just depends on which one you think is easier to read. Textbook is recommending that one. I would do the same. I would recommend that one. If you have to have more than one choice and you wrote it as a not equal, go ahead and flip the logic so that, it's checking for the equal case first rather than the not one. But it's a judgment call, not a hard and fast rule. So if customer age is greater than or equal to 65, then the discount is equal to 10%, else the discount is equal to 0. End if. This is the action taken if this expression evaluates the true, if the condition is true. If it's not, that's the value that it gets assigned if it's not. Or you could reword it. The opposite of greater than or equal is less than. So if you wanted to flop the logic, use the opposite operator. If customer age is less than 65, then do the second thing, else do the first thing. Yeah, I don't see a reason to go for one or the other. I don't see a compelling argument. It's just identical logic. You could go either way. You pick a way that makes sense to you. Avoiding a common error with relational operators. Using the wrong operator. Alrighty, that would mess you up, right? If you use less than when you meant greater than. More importantly, missing the boundary or the limit required for a selection. Right? What if they're exactly 65 years old? Should they be allowed the discount? Probably so. So you'd want to do, greater than or equal to. If age is greater than 65, give discount. What if they are 65? Do they get it? You'd ask. You'd ask the person writing the specs, and they'd probably say, yeah. Probably, yeah. So, write as if age less than or equal to 65. So when you're writing your expressions, your relational expressions, just make sure you figure out how to handle the boundary, right? Whether 65 is supposed to be part of it or not. We saw a similar thing up here when I was talking about when you were doing, if x is less than 0 and x greater than or equal to 0. If you don't handle the edge case right, if you don't handle the boundary case right, then, it won't work when that value is at that boundary. So you just have to think it through. So that's a problem, missing the boundary of the limit required for the selection. So ands, known as a compound condition. Ask multiple questions before an outcome is determined. That doesn't mean a lot to me, maybe it does to you, but it's pretty easy to understand what it really means. Requires that both of the two tests evaluate to true. So, if A and B, this means that both A and B have to be true for the expression to be true. And I need to keep remembering to capitalize true and false just because that's what Python wants if we type those words into Python. So, if money greater than 0 and hunger greater than 0, eat out. Right? They both have to be true. That's what and means. If only one of them is true, you're hungry but you don't have any money, well, you can't go eat out unless you can convince a friend to take you out. If you have money but you're not hungry, then you're not going to go eat out. Unless you just want to go, for the company. Anyways, so both of these would have to be true. This case would have to be true, and this case would have to be true. On the other hand, you can have or. If sick or tired, stay home. Only one of those has to be true. If you are sick, stay home. If you are tired, stay home. Whereas this one was if you have money and you have hunger, only then do you go out, eat out. Hope that makes sense. Now I'm going to get all logical and put up what's known as a truth table here. If you have two cases like this, if A and B, so we have two variables, A and B, and we are hooking them up with ands. Here's the result. If A is false and B is false, then the result is false because they both have to be true for the answer to be true. If A is false but B is true, then are they both true? No. So it's still false. If A is true and B is false, are they both true? No. When is the only time an and works? It's when they're both true. And yeah, I could type out the entire words. I think just F and T will do for our sake, right? Okay. That's the and truth table. There's another one for or. If you're doing or logic, if I'm sick or I'm tired, only one of them have to be true for the result to be true. So here's the or truth table. Again, you have two inputs, and you have the or keyword, and here's the result. So you have two falses, but one of them has to be true. So since neither one of them are true, the result is false. How about if you have a false and a true? Yeah, that's a true. Just like if you have a true or a false, that's a true. And then if you have a true and a true, that's a true. All right, and you guys who are in engineering courses may have heard of exclusive ors. I'm not going to talk about them much, but an exclusive or means that one or the other, but not both, are true. I'm never going to use an exclusive or in that class, but if you've ever heard that phrase, that's what it means. So the truth table for an exclusive or would have that one be a false because it means if one or the other, but not both, are true, then the result is true. And that's used for circuitry designing. Okay, so if you have an and decision, it is a shortcut to writing something like this. If hunger greater than 0 And then if that's true, if money greater than 0, print, let's eat out. Right? This is known as a nested if. Which you could write just as easily as if hunger greater than 0 and money greater than 0. Print, let's eat out. So you can use and to eliminate nested ifs sometimes. Hope y'all see that those are the same thing, right? Because this had to be true and this had to be true before we could print let's eat out. That's why we would use and. Or is a little bit different. You don't use or to replace nested ifs. You do it like this. If sick, print stay home. If tired, print stay home. You see that? You could reword that as if sick or tired, print stay home. And I forgot to put my end ifs. Right? So the or is replacing repeated if statements that have the same result. If you have several if statements in a row and they're all producing the same end result, you can combine them with an or. If you have several nested ifs before something finally happens, you can replace those with an and. So you can use or to replace repeated conditions that result in the same outcome. Just like this. Here we had two things that printed stay home, so we just chained them together with an or. And that's almost making it more complicated than you really need, but you know the way computer books are. We have to pound things in. Wrong. Alrighty, efficiency. Efficiency isn't our main concern when programming in Python because Python is not a fast language. It's not the tool that people would go and write Call of Duty in. You know, that would be written in C++ because C++ is pretty much the fastest language except for writing in assembler. But if you are concerned about efficiencies, then there are some things to be concerned about. If you have something like this, if A, if B, do something. Every comparison takes a little bit of time, you know, a millisecond, a nanosecond, or whatever. This logic could be just the same written like that. You know, I think those end ifs actually make it harder to read than easier. I'm going to leave them off. You understand that they're there. Okay, so these actually do the same thing right. Both A and B have to be true before you do something. But what if you're trying to minimize the number of comparisons? Because each comparison, you know, the chip has to go and access a spot in memory and read it in, you know, but have those two numbers in place before it can do a comparison. So what if A is true 10% of the time and B is true 90% of the time? Which one would be a more efficient way of writing it? You want to put the thing that happens least often in the beginning. Why? Because if A is only true 10% of the time, we don't want to be testing B over and over and over and over. We don't want to do the second test if the first test is false. So you arrange it so that the most exclusive test happens first. So like if people are all lined up into a club and you had two rules. One, you have to be the age of 18, and two, you have to have, you know, I don't know, purple shirt. Which one's easier for them to C as you're walking up. The shirt's the easy thing to rule out, right? Because you're just looking at them. So, if purple shirt, and then if age is 18, let into the club. Not vice versa. You're not going to ask them their age and then look at their shirt because it's easier to identify, it's less time. That was a stupid parallel. Sorry. Anyways, what you want to do, and I'm not going to ask this on an exam, but it's good to be thinking about programming efficiency. Just don't sweat it too much. Generally, the rule is write a program to be easy to read, and then only if it runs too slow do you then go back and worry about efficiency. But if you're doing something like this, make sure, if you care about efficiency, that you put them in the order of least likely to happen to most likely to happen in your if statements. And the same is true of and. Since this is the same as writing this, if A and B do something, same guideline. Make that the most exclusive situation. Make that one the least likely to be true, so that it won't even bother checking the next one. And this one is the same as writing if B and A do something. Same idea. So if I have two expressions, A is equal to 100 and B is equal to 50, and I know that A is a lot more likely than B, and I want to write if both are true, then do something. In what order would I put it? Remember, I put the least exclusive first. Excuse me, I put the most exclusive, the least likely one first. So I would put if, which one is the least likely? Yep. So I would do that B is equal to 50, and then I'd put the and A is equal to 100. I should have been using double equals, since that's how you compare. All right, enough about efficiency. That speeds up processing time by eliminating as many instances of the second decision as possible. It's possible I could ask that on the exam. If it shows up on the MindTap test, then it's fair game for an exam. All right, we haven't actually done any code today. Using the AND operator, you just ask two or more questions in a single comparison. We've already had some examples of that. The truth table describes the truth of the expression based on the truth of its parts. You can make a more complicated truth table. I'll give you an example of a more complicated truth table. What if you had if A and B or C? Well, then you have three variables, right? And now I'm going to switch to doing zeros for false and ones for trues. So if you had A, B, and C, you have more than just four possible states. This looks like our binary odometer, right? So three Boolean variables give you 8 states. 4 Boolean variables give you 16 states. Now I'm not going to actually work out the truth table for this. I'm not going to go through. I know this one's false. Don't know about the rest of them, right? So I'm not going to. However, just like we have rules of precedence for multiplication and division and addition and subtraction, there are rules of precedence for and or. In the rule of precedence, and is done before or. Why? Because and is in effect multiplication, and or is in effect logical addition. And let me show you a truth table that'll kind of prove that point. We're going to set up another and truth table, except I'm just going to use zeros for false and 1 for true. Now since we're doing and, they both have to be lit up before we ever get a true. So 0, 1 is a false, a 1 or a 0 is a false, and a 1 or a 1 is a true. That's the and truth table. Notice if you put a multiply sign in there, it would look just as good. Where's the asterisk? Right? That's a valid table. 0 times 0 is 0. 0 times 1 is 0. 1 times 0 is 0. 1 times 1. So and is the equivalent of logical multiplication. I'm just going to make that term up. If you ever go and take a logic class, you will see people write logical expressions in the form of using multiplying as the and using addition for the or. So let's do the same truth table for or. Okay, so the same idea. We have 0 and 0, 0 and 1, 1 and 0, 1 and 1. Since we're doing or, only one of them has to be lit up for the answer to be true. So if they're both false, that's a 0, but if one of them is a 1, if the other one is a 1, or if they're both 1, right? And this looks a lot like addition. 0 plus 0 is in fact 0. 0 plus 1 is 1. 1 plus 0 is also 1. Now 1 plus 1, okay, that's a little bit different, but just remember that in the Boolean world, there's only 2 possible values, 2 possible numbers, 0 and 1. So that's why 1 plus 1 is equal to 1, because it means not false, right? So hopefully we can see that or is the equivalent of logical addition. Or equivalent, not result. I'm just going to say or is akin to addition, right? And is akin to multiplication. And like I said, if you ever go and take a course in logic, then you'll see a lot more of that. But that is why ands have to be done before ors. Because what happens first, multiplication or addition? Multiplying. So since ands are akin to multiplication, and ors are akin to addition, that's why the ands have to be done first. So if you have this expression, if A is equal to 0 and B is equal to 0 or C is equal to 0, which parts of them are grouped together? Well, just like in multiplication, the and gets done first. So we would evaluate all that first. And then if that evaluates to true, then we would compare it to that one. That makes sense? So the and the ors dictate the order in which the expression is evaluated. It's not just left and right. Just like if you do this, A is equal to, 3 plus 4 times 5. You know which one you have to do first. You have to do that first. So if you have this expression, you would have to do this part first. So I did have an expression up here that I'd written, if A and B or C. We could figure it out. This is the part that has to be done first. Now, I'm not going to take the time to figure it out. I'm not going to take the time to write the truth table for this expression. If the PowerPoints start hammering in on the evaluation of logic, then maybe we'll come back and we'll do a truth table for an expression like that. I don't remember having to do that in my 2-year college courses, just in my 4 ones. We'll see what the book has to say about it. Okay, so short circuit evaluation is how things get skipped if only one part is true. Remember if we said this, if A, and then we did if B, then do C. If that's not true, then this is skipped, right? That's called short circuiting. So if you have if A and B, do C, short circuiting means that if this is false, this evaluation is skipped. Short circuiting sounds bad. Captain, the engines have short circuited. It's not bad. It's a time saver. if part of the expression of the and is false, don't evaluate the other part. Now that's for ands. For ors, the rules are a little bit different, right? Because if you have this, if A or B do C, you can't rule it out based on this one, right? Because even if that's false, you still have to come over here and check. But what if it's true? Do we even have to check the second thing if we're doing or? No, we don't have to do the second thing, right? Because if the rule is if sick or tired, stay home. If you're sick, you don't even have to ask yourself if you're tired. So, short-circuiting for an or means, let's write these a little bit more clearly. Short circuit for and. If the first operand is true, is false, then skip the second. Short circuit for or. If the first operand is true, then skip the second. Because if that one's true, you don't need to think about it. You already know that you're going to do C. So I've just restated it, in textbook style, talking about operands. Just the same rule. This is all just saying what we've already talked about. Both expressions must be true for the result to be true if you're using and. Let's go ahead and write a little bit of a program just so that we have something to upload for today. We're going to be using and or. So I'm going to do file is equal to new. File, save as. Call this March 14th. So we're going to ask the user a few questions. We're going to ask them 4 things. Age is equal to input. What is your age? And then we have to convert it to a float because I'm doing real programming, age rather than pseudocode. And then let's do another one. Money is equal to input how many dollars are in your pocket. Let's also convert that to a float. And then let's ask a few more questions. Sick is equal to input, are you sick? Y/N. And then tired is equal to input, are you tired? Question mark, Y/N. So now we have several variables to play with. And we're just going to write the same ones that I've been putting in my notes. I didn't ask about hunger though, right? So let's do that. Hungry is equal to input, are you hungry? Question mark, Y/N. Now we have all sorts of variables we can play with. So, like going into to see the R-rated movie, we have to be older than 17, unless accompanied by our parents, and we have to have money. So, if age is greater than 17 and money greater than 0, I'm assuming we can get into the theater, you know. And let's say $5. This is a $5 ticket. Then print. Okay. Go to the movie. Else, print, no movie for you. Now let's do the money and hungry one. If hungry is equal to y, because that's what we told them to type, and money is greater than 0, we're going to assume that you can go out to eat even if you have 1 red cent. Print. Let's go out to eat. Else, colon, print. Let's stay home. Or let's rewrite that. Don't eat out, stay home. Now let's use an or. If sick or tired, then stay home, else go to work. So if sick is equal to y or tired equal quote y, print stay home and rest. Else, print get up and go to school or work or whatever, you know. So I've made a mistake in my logic right here. If this is a $5 ticket, then how should I have written this if statement? Remember when I talked about the boundaries?
If you are 17 or you have only $5. Greater than or equal to?
Yeah, it needs to be greater than or equal to, because if, as written, if I had $5, it still wouldn't let me into the movie because I said money is greater than 5. So it needs to be greater than or equal. All right, let's give it a shot. Let's see what happens. What is your age? I'm 20. How many dollars are in my pocket? 1. Am I sick? Nah. Am I tired? Nah. Am I hungry? Yeah. No movie for me. I didn't have enough. Let's go out and eat and get up and go to school. I'm going to run it again, and I'm going to say that I'm sick or that I'm tired or that I don't have any money, something like that. What is your age? I'm 10. How many dollars are in your pocket? 10. Am I sick? Yeah. Am I tired? Nah. Am I hungry? Nah. So no movie for me. I'm too young. Don't eat out. Stay home because I wasn't hungry. And stay home and rest because I was sick. So maybe some of the expressions should have been more complicated, right? If we're sick, we probably shouldn't be going to the movie. And, if we're sick, we probably shouldn't be going out to eat. So we could try to write a more complex expression using both ands and ors. So why don't we do if sick is equal to y, or tired is equal to y, or, I'm not even coming up with a good example, but you saw what I mean. Maybe going out to eat should also check to make sure that they're not sick or tired. And we could tack some things on to make sure that that was not true. Just to play with that. You see those 3 lines there? Those 4 lines there? I'm going to copy those. And I'm going to play with the logic, writing it a little bit more complicated so that we don't go out to eat if we are sick or tired. Here's one way to do it. If sick is not equal to y, and this is going to be a complicated way of doing it, and tired not equal to y, and hungry equals y, and money greater than 0, let's go out and eat. Now that's a few too many nots and ands and stuffs like that, right? I don't think that that's a good way to write it. But logically it does what I want. I hope. Let's find out. Sorry guys, I'm covering up the screen. Maybe I can put some enters at the bottom. All right. So what's my age? I'm 20. I've got a lot of money, but I am sick. I'm not tired, but I am sick. I sure am hungry. And it did turn out to say, don't eat out, stay home. But this is a pretty gnarly expression. I wouldn't want to write it like that. If I could write it in some other way to simplify it, I would try to. Now looking at it, I'm not seeing a great way of rewriting it. One of the things I don't like about it is that it uses not equals rather than equal equals, because like I said, when you start hitting negatives, then your brain has to do kind of a little flip in order to get it to work. I'm not going to even rewrite it. I'm just going to leave it like that. I will put a comment, though, that really we shouldn't go out to eat if we are sick or tired. So, all right, let's make a Dropbox for this. Yes, absolutely. Yeah, I didn't do a walkabout, make sure everybody was up and running. Let me do that. So we have a Dropbox K. Put your file in it, refresh. Once you're done with that, great, go ahead and have a great break, y'all.